Welcome to another exercise in the workbook Statistics. This time I'm going to talk about how to test for stochastic independence, or rather discuss an exercise on exactly this topic. So let's have a look at the exercise. Here we have a hotel asks their guests which services they rate as the most satisfactory, in addition to their gender. In the course of the next month, the following data has been collected. We got this overview here, with the two genders and with three different service sectors. Our task now: conduct a suitable test at a margin of error of 5% to check whether a significant relation between the gender and the best rated service exists. Well, this calls for a classical chi-square test of stochastical independence. And well, how do we get about this? Well, first I'm going to copy this table and expand this slightly. So I'm going to copy this and I'm adding a row and a column for the marginal frequencies. Marginal frequencies, that's actually nothing else than the row and column sums. So here I'm going to add up all the entries for male, all the entries for female. Then I'm going to add up all the entries for bar, restaurant, and animation. Finally, in the lower right one, I'm going to add up either male and female or the three service sectors, and I should end up at the same value. So in both cases the sums result in 220. And that's actually the first step I need, because in the next step I have to calculate the so-called expected frequencies. So whereas this here is the actual distribution that I'm faced with, in the next step with the expected frequencies, I take a look how, assuming that only the marginal frequencies exist, the distribution should look like to be as uniform as possible. Well, as I said, I'm going to calculate the expected frequencies. How do I do this? And that's with this formula. This formula can actually best be explained on the table or with the table itself. So I'm first going to copy the table as is, but I'm leaving the frequencies blank. And then for each entry, I'm going to multiply the respective column and row sum, or marginal frequency. So here for male and bar, I'm going to multiply the 110 for male with the 48 for bar. And this result I'm going to divide by 220. And this looks as follows, giving me an expected frequency that in this group there should be 24 males or people. Well, I'm doing this for all the entries. For example, here with restaurant, I have here 49, 110 again, and the same 220, giving me here an expected frequency of 24.5. That's not an integer, but this doesn't matter. So expected frequencies usually are not integers, which in the end is not a big deal as such, because they're just theoretical values. Well, for animation, similar, it's 131 times 110, so these two values, divided by the 220. And then we can do the same stuff for female, since females also have 110 representatives in the sample. It looks more or less exactly the same to the column for males. But in either case, it's always like I'm doing a big rectangle here. So one corner, that's what I'm going to calculate anew. The other two corners, those two here, that's what I'm going to multiply on top of the fraction line. And the last corner, the opposing corner to what I'm calculating, that's what I'm dividing by. Well, now I have the expected frequencies and can actually compare expected and actual frequencies. That's why in the next table I'm just going to summarize actual and expected frequencies. Well, it looks as follows. Based on these numbers, I can calculate the chi-squared statistic. There's a structure to this. So for each of these entries, I'm going to calculate one term. So I could also copy the same table again and then fill in step by step by step or field by field by field by field. Here I'm just going to write this down in one line so that it can also fit on the same slide as this overview. So taking the first one, males and bar, I have the expected frequency and I'm going to subtract the actual frequency. The result then is squared and divided by the expected frequency. Then I'm going to do this for all the other ones as well. Here, expected 24 minus actual 14 squared divided by expected 24. That was the first row. Then I'm going for the second row. That's the 24.5 minus 12 squared divided by 24.5. Well, that's what I'm doing for all of my different entries. And finally, I'm going to sum all of this up. This yields me, with this intermediate step, a chi-squared test statistic of 21.1574. That's actually the statistic which in the next step I'm going to compare with my reference statistic. Well, for this, first off, I need a reference statistic, so that's what we're going to do next. The chi-squared statistic, I'm just copying this here so that we have this present. And the reference statistic, in this case, is the statistic chi-squared I minus 1 times j minus 1, then 1 minus alpha. I, that's the number of rows, j is the number of columns. So here I have 2 columns, 3 rows. So I have 2 times 1, giving me 2 here. And then I have 1 minus alpha. Alpha, that's the margin of error. That's here 5%. So I got 1 minus 0.05, giving me the 0.95. Meaning, in the table for the chi-squared distribution, I'm going to look up the value chi-squared to 0.95. There I'm finding the value 4.9915. So that's the value I'm going to compare the test statistic with. That's my test decision. So I'm comparing these two values and I see that the test statistic is much larger than the reference statistic. This means I can reject my H0 hypothesis. In this case, the H0 hypothesis means that there is no relation between the two variables. So since it's rejected, the opposite is true. Here I can say a significant relation exists between the gender and the evaluation of the different service sectors. Well, I cannot say what the structure is, so whether one of the two genders is more in favor of one or the other, but I can say there is a relation between gender and different sectors. Well, that's then everything there is to this exercise. I hope you enjoyed it. I say goodbye and see you next time.